Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 41 on the subject of computer organization and assembly language programming. The title of today's session is GDB with PEDA plugin. This slide shows today's agenda. First, we will have a quick recap on debugging with GDB, which we have been doing in this course. Then we will download the PEDA plugin, Python Exploit Development Assistance to GDB to enhance the firepower. Today I will not go into the details of reverse engineering and exploit development power of this plugin. Rather, I will restrict myself to acquaint you all to its basic environment. The basic environment of PEDA with special emphasis on understanding the working of process stack. Finally, I will demonstrate with the help of an example assembly program. So first, let us have a quick recap about debugging and the GNU debugger GDB. Well, you all know that a debugger is a program running another program. Some example debugging programs are the famous GNU debugger GDB, Radar 2, which is a complete framework for reverse engineering and analyzing binary, the interactive disassembler IDA, immunity debugger, soft ice, and the list goes on and on. In this course, we are using GDB, which is a portable debugger that can handle the assembly of processors like IA32, the AMD x86-64, ARM, Advanced System Machine, mostly used in embedded devices, MIPS, microprocessor without interlocked pipeline stages, and Sun scalable processor architecture, SPARC. Well, GDB run on most popular Unix and Microsoft Windows variants, as well as on the Mac operating system as well. And GDB work for many different programming languages, including Assembly, C, C++, Objective-C, OpenCL, Go, Modular 2, Fortran, Pascal, and PEDA, to name a few. Well, during this course, we have used GDB's command line interface and text user interface to understand what is going on inside our assembly programs while they execute. And we have also manipulated the flow of program execution. Well, dear students, we can use GDB for reverse engineering, cracking binaries, and exploit development as well. However, GDB do not have commands for exploit development and has weak scripting support. So to enhance the firepower of GDB for analyzing, exploiting, and doing reverse engineering of executables, hackers use GDB plugin called PEDA, the Python Exploit Development Assistance. And this is the topic of today's session. Well, this slide summarizes as to how you can download and use PEDA plugin with your GDB. Well, to use PEDA, your Linux system must already have a GDB version 7 onward. And remember, I think the latest GDB version as of today is 10.7. Other than having a pre-installed GDB on your system, you must also have a Python version 2.6 onward. And I think the latest Python version as of today is 3.9. Let us visit the GitHub repository for downloading PEDA, github.com, long LD PEDA. Well, this is the repository. Well, dear students, Python Exploit Development Assistance plugin for GDB provides a whole lot of commands that hackers use for exploit development. But in this course, we will be using it for the enhanced display of GDB. And the display you will get, this is one of the screenshot of the display. You will get 4 sections once you run GDB with PEDA plugin. the register section, the code section, a portion of the running stack, and at the very bottom we have the command section showing the commands as well as some messages. Well, dear students, these are the installation instructions. Let me zoom it. These are the installation instructions. You just need to clone this repository inside your home directory, inside a directory PEDA. Let me copy this. And after doing that, you just need to append the path of this file peda.py in the GDB initialization file inside your home directory. So let us move on to the Linux terminal and do this. Okay. So I am Arif. I am Arif inside this lecture course 41 directory. Let me paste the command that I've just copied from there, which is going to clone this repository inside a directory named PEDA in my home directory. So this is quite small. This is done. Let me show you the contents of this directory PEDA inside my home directory. These are the contents. The entire repository has been cloned over here. All the files are downloaded. Now we just need to mention the path of this Python script peda.py in the GDB init file, which is a hidden file inside your home directory. Let me open it up. .gdb init inside my home directory. If this file exists, it's okay. If it doesn't exist, just write down this simple line inside it. Source, source, and then the path of that file inside my home directory, inside the PEDA directory, and over there peda.py. Sorry for the typos. Well, this source command is mandatory to mention over here because it is used to run this Python script inside the current shell process. Let me save and exit, and let me confirm whether the file has been created or not. GDB init. Well, the file is there and the path is also there. Let me clear screen. Okay, now whenever we run GDB, it will first read the .gdb init file, and since the file contains the line containing the peda.py script, so GDB will run with the PEDA plugin. Let me press GDB, and you see you have a different prompt over here this time. So this shows that the GDB is running with the PEDA plugin. If you want to disable this, you don't want the PEDA flavor of GDB, you can just comment the line inside this configuration file GDB init. If you delete or comment this line, the GDB will run in its vanilla flavor. Anyways, well, dear students, this is the same GDB and all the commands of GDB that we have been using so far work over here as well. For example, help. So this is the help command that shows different classes in which standard GDB commands are categorized. And if I want to view the commands related to, let's suppose, the running class, I can type help running. So these are all the commands related to this, and within this, if I want to just check out information about the command si step in, well, that is used to step one instruction exactly. Well, in GDB with PEDA, you can run many of the shell commands as well. Like clear is a shell command, you can use it over here. PWD is a shell command, you can use it over here. Well, cat is also a shell command, and you can use it over here. Dear students, the way you can get help about the GDB commands, you can get help about the PEDA specific commands as well. And to get a list of all PEDA specific commands, you just type PEDA help. So these are the PEDA specific commands related to analysis of executables, reverse engineering, and so on. Well, no one memorizes these commands. You just use them whenever you need them. And mostly used commands are automatically memorized. Let us quit and fall back to the slides. Well, we are done with this. And we are done with the demonstration of downloading PEDA and using GDB with PEDA as well. Okay, dear students, before we load and execute an assembly program inside GDB with PEDA, let me first describe the program which we are going to load in a short while with an illustration for better understanding. Well, this is the program. This program performs a move and an XOR instruction in the very beginning after the start label. Then it carries out 3 push operations with the immediate values on the process stack, and later perform 3 pop operations to remove the 3 values in the last in first out order inside the registers R11, R12 and R13 respectively. And finally, these 3 instructions make the exit system call to exit the program gracefully. And here is the stack portion only of the logical address space of a process. And we have discussed the working of a process stack in lecture number 33 as well. Well, dear students, in a process logical address space, the stack is at the top of the memory and grows from higher addresses towards the lower addresses in architectures like Intel, MIPS, Motorola and SPARC. Well, the stack pointer RSP always contains the address of the current top of the stack. That is, it points to the last inserted item on the stack. And one more important thing is that the width of the stack in x86 64 is 64 bits. So all push and pop on the stack are 8 bytes wide. Let us just assume that when this program starts its execution from this line, that is this move instruction, the stack contains these 4 hypothetical items. And the RSP register, also called the stack pointer, is pointing to the top of the stack, that is the last inserted item. Well, these first 2 instructions, this move and XOR, does not have any impact on the stack as they just work on these registers. However, when this first push instruction executes, that is push 65, this RSP will be moved 8 bytes towards the lower address, and a 64-bit value, decimal 65, will be pushed on the stack. And this is shown pictorially over here as well. You can note that this hex 41 in 64-bit has been pushed at the top of the stack. Similarly, this push 66 instruction will move this RSP further down and place another value on the stack. And then this third push will also moves the stack pointer 8 bytes down and places another value on the stack. Also note that these 3 values 65, 66, 67 are the ASCII codes of capital alphabets A, B and C. Although single byte, however, every push will place a value of 8 bytes or 64 bits on the stack. Well, finally, these are the 3 pop instructions, and each pop instruction will pop an 8-byte value from the top of the stack where our RSP is pointing, uh, and will remove these values and place them in appropriate registers. And meanwhile, after every pop, this RSP will move to its previous location, that is 8 bytes up towards higher addresses. So first we will do a pop R11. So this 43 will be removed from the stack, placed in R11, and this RSP will move up. Okay, now this pop R12 will remove this value, that is hex 42 or B, place it in R12, and this RSP will move up. And finally this pop R13 will remove this value, place it in R13, and the RSP will move up. Do note that these pops are in reverse order. That is, this C will be popped first, then this B will be popped, and finally this A will be popped. So that is why we say that this work in last in first out order. And finally these 3 instructions will exit the program gracefully. Okay, so now let us move on to the Linux terminal and execute this program inside GDB with PEDA. Let me clear screen first, and let me show you the code of example.nesm that we have just discussed on the slides. This is the same code, the 2 move and XOR instruction, the 3 push instructions, pushing immediate values on the stack, the 3 pop instructions, and finally the 3 instruction that makes the exit system call. Okay, so let me assemble this program. nesm-f elf64-g example.nesm. Let me link it, example.o. So we have generated the executable with the name of a.out. Let me load this in quiet mode inside GDB, and since we have the PEDA enabled, so you can see the different prompt over here. Okay, so we can always put a break at start, and then we can run. So let me shrink the screen a bit to acquaint you with the bigger picture of the layout of the running of the program. These are the 4 sections. First of all, the register section at the very top, showing the 16 general purpose registers, and this E flags register having right now only the interrupt flag set, as it is shown in bold red color. The rest are 0 right now. After this register section, we have this code section showing the disassembly of the code. Note that the next instruction to be executed is shown in green over here, this move instruction, which is the first instruction at the start label. Also note the logical address of the code section and the arrow showing that this is where the RIP register is pointing. So this is the current instruction containing the address 0x401000, and you can note these are the contents of the RIP register as well over here. Okay, great. Well, this is the third section, that is the stack section, showing a portion of the stack. Let me zoom it a bit so that you can understand it. So this is the stack in which we are interested in particular in today's section. These are the 48-bit logical addresses, and the contents at each location are also shown. Well, do note that in x86 architecture, the stack grows towards smaller addresses. So over here, the stack is growing like this in the upward direction. we have A0 address, then we have 98, then we have 90. So stack will grow towards smaller addresses, from higher addresses towards smaller addresses. Right now the top of the stack is over here at address E090, and the same should be the contents of the RSP register as well. Let me move up. Okay, so you can see that the RSP register also contains the same address. So RSP is pointing at the top of the stack. This is what we have seen in the on the slides in the illustration as well. Okay, so at the very bottom over here we have the fourth section and the last section. This shows the source code of the next instruction that is going to be executed. And do note the difference between the source code assembly move RAX, 255 and the disassembly move EAX, FF. A minor difference you can observe. Anyway, so this was the description of the colored and beautiful layout of GDB when you run it with PEDA. And before I step in and execute this currently loaded process, let me run some basic PEDA commands as well. Get PID, this is a PEDA specific command that is used to display the ID of the currently running process, PID of the currently running process. Proc info to get information about the process. This is the executable. This is the complete path of the program which is currently loaded. These three lines shows the three file descriptors: std in, std out, and std error. And these are some of the IDs of the process ID, its parents ID, the user IDs, and the group IDs. Okay, let me show you another command, check sec. Well, this check sec command shows some security protection mechanisms that are in place for this process right now. We will discuss them some other time, but however, let me just name them and describe them in a single line for you. A stack canary is a value that is used to detect the overwriting of a function return address to protect from a buffer overflow. This 45 source is a macro that detects buffer overflow in functions like getS and strcpy. This NX non-executable bit, this is used to make the stack, heap, and data section non-executable. This pi is position independent executable that actually prevents the return to libc attacks. You may come across such attacks when you will dive deep inside the hacking world. This relro is relocation read only. This is also a protection mechanism that makes the GOT, that is global offset table, read only. And other than these, there is another protection mechanism not mentioned over here. That is ASLR, address space layout randomization, which is an operating system security mechanism that randomizes all the addresses of an executable process every time you execute it. Okay, well, let us restrict ourselves to executing a program. Let me clear the screen and let me do SI. I think as I have already placed the break and run the program. So this is the instruction which is going to be executed right now, XOR. Let me shrink it a bit so that you can see all the four sections. So XOR will perform an XOR on the RAX contents. Right now the RAX register contains FF. Let me press SI again. You will see the contents of RAX will be zeroed out, and yes, RAX contents are zeroed out. Now we have the push instructions. Please keep a note, this is the first push instruction that is going to push hex 41 on the top of the stack. And right now RSP over here is pointing at address E090. So it will move to 8 bytes to lower address, and then it will place a 4-1 over there. Let me press SI. Note that A has been pushed onto the top of the stack. Let me press SI again to perform the next push. Let me press SI again to perform the next push. All the 3 pushes have been done. You can note that the data has been pushed on the stack, and the last item that we have pushed is hex 43, which is at the top of the stack right now. Now we are going to do the pop operations. This pop R11 will pop an item 8 bytes data from the top of the stack and will place it in register R11. Keep a note of the register R11 over here, and keep a note over here as well, and keep a note of the RSP as well. The RSP will of course move down after this. So RSP has moved to address E080, and now at the top of the stack containing B, R11 will be containing C. That's great. And now this B will of course go inside R12 for the next pop instruction. Note the B has gone inside R12. Note the top of the stack contains just one item, that is 41. Top of the stack is at address E088. RSP is also pointing at E088. Let me do SI again, and finally this A has also been moved to R13. Great. And the stack is at the same old location from where we started. And finally these are the 3 instructions that are going to call the exit system call. Let me press C to continue, and there you go, the process terminated or exited normally. Let me press Q to quit, and let me fall back to the slides. Okay, so that is all for today's session. My dear students, please do practice this, because in all the future sessions we will be using GDB with PEDA, which will really be helpful in understanding as to how function calls are made in assembly and other high-level languages. And we will be understanding this by visualizing the stack inside GDB. I hope this session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning, and Allah Hafiz.